Hello everyone, welcome to section 4.3 on logarithmic functions. Okay, let's kind of recap where we've been and hopefully that'll kind of guide us to where we're headed with logarithmic functions. Now, there are two main things I would say recently that we've been talking about. We've been talking, one, about a very special type of function in mathematics, exponential functions. So we've been talking about, write it up, exponential functions. Okay, exponential functions, f of x, which is equal to b to the x. We have conditions on the base. The base has to be greater than 0, and the base can't be 1. We know a little bit of something about their graphs. So we know that if b is greater than 1, we have an exponential growth model. Exponential functions have asymptotes. We have a horizontal asymptote. The function grows if the base is bigger than 1. But if the base is a fraction, we have a decay model. We'll have a decay model. So the function will get smaller. Okay. So here we have these exponential functions. These are great for so many things. Population. Population grows exponentially. Money in your bank account grows exponentially. Also, a lot of things decay. I don't know, you could think like, I don't know, this would be like half-life or so I don't know, maybe you have a bunch of bacteria on some moldy bread and you kind of like, I don't know, you spray it with some like Clorox or something, or I don't know, it's some bleach. I don't know, you bleach the bread, you try to kill the bacteria, and maybe every minute the population halves. So initial population, then the population gets halved, and it gets halved, and it gets halved, and it gets halved again. The population will be decreasing. We have a decay model. Okay, so these are very important to science, but there's also something else we've been learning about. So it's not just exponential functions. It's not just exponential functions. I guess maybe I should also comment that we learned about a very special number e. We learned about a very special number e, and we could talk about the it's called the natural exponential function e to the x. Notice here that e is roughly 2.718. So if we're thinking about the function e to the x, this function is all over calculus. This thing is all over the place. The exponential function, e to the x, well, that's going to be a type of growth model. This is, again, what e to the x would look like. And specifically, if you plugged in 1, and I guess if this is 2, and this is 3, in this case, if we were to graph this, if we were going to graph the exponential function, e to the x, okay, if you plug in 0, you'll get out 1. Here's 2. Here's 3. If we plugged in 1, the output would be roughly what? 2.7-ish? So here, every exponential function goes to the point 0, 1. So here would be the function e to the x. Very important function. This is the point 1 and e. Okay, but it's not just exponential functions we've been talking about, not just exponential functions. We've also been talking about inverses. Okay? We've also been talking about inverses. Okay, so for example, let's say we have a function f of x. Let's say, for example, that it's x cubed. We can figure out what the inverse function is. You can kind of think here as inverses as something that undoes something. So if we cube a number, how do we undo cubing a number? We'll cube root it. So the inverse of this function is the cubed root of x. Now, this symbol, the cube root, I think that the notation for this inverse has to remind us where it came from. I have the function x cubed. I have a 3 here. The notation we gave for its inverse, the root, we kind of put this symbol here, and we put this little 3 right here that should remind us that this is the inverse of cubing. Similarly, we could have something like, 5 to the x. What would be the inverse of this function? Well, we denote them. They're called roots. And that would be the, how about instead of f, I write it as g, just a different function. G and g inverse. This would be the 5th root of x. And what's great about inverse functions is that they undo one another. When I compose them with themselves, we just get out what we started with. So for example, if we take a function f of x and we compose it with its inverse, What is it saying we're doing? We're taking a number, we're cubing it, we're taking a number, cubing it, and then what are we doing? Then, guess once we cube the number, then we're gonna cube root it. Then we're gonna cube root it, and they cancel each other out. We just get back out x. You cubed a number, you cube root it, you're back to the number you started with. This would work the other way. Even if you first cube rooted a number, and then cubed it, so if we cube root a number, take a number, cube root it, and then after you cube root it, you cube it, you're going to get back out x. So what's great about functions is they undo one another. Now, why is it nice that we can have a function that undoes something? It's great for solving equations. It's great for solving equations. If we have an operation, we want to undo it. We want to apply an inverse function to it. So, for example, if we're trying to solve the problem, I want to know when is 9 equal to x cubed plus 1? Well, I want to undo the operation of adding, so we apply the inverse operation. We subtract 1 from both sides. So there's an inverse to adding a number. Okay, how do I took a number and I cubed it. I want to apply the inverse operation. We want to apply the inverse operation. So we apply the inverse to both sides. So we'd have that x would just be the cubed root of 8. Or x would be, what? 2. So inverses are great for solving equations. But think about what we've been doing. We've been working with exponential functions. We've been working for exponential functions, and there's a lot of great equations we'd want to solve for exponential functions. Remember when we were talking about zombies? And they were doubling, their population was increasing by 100% each day. Remember that the zombie function was 2 to the t, or we could say 2 to the x, just a different variable, 2 to the x. This is an exponential function, and maybe we want to know how long would it take. Maybe I will put a t here. This would be like we want to know how long would it take for the zombies to overcome Bellingham? How long till the population is equal to the Bellingham population? We want to understand this so we could, plan. Or maybe you're saving up money. Maybe you want a Lamborghini. Maybe you somehow saved up $8,000. And then maybe you find a sweet bank account. That, has 8% interest. Maybe it has 8% interest. Maybe it compounds monthly. And you'd want to know, well, how long would it take for us to have enough money for a Lamborghini? Or how much is a Lamborghini? Like $500,000? We would want to solve this equation for t. These are exponential functions. We don't know how to undo exponential functions. So what do we need to be able to solve equations like this? These are great applicable equations we'd want to solve. Well, we need an inverse. We need an inverse to exponentials. And what are the inverses exponentials called? Logarithms. They're called logarithms. That's what we call them. And that's the topic here. We want to be able to solve exponential equations, so we need an inverse of an exponential. So we want the inverse, and we're going to call them logarithmic functions. So that's where we're headed. That's what we want to do. So let's talk about them. Let's say that we're doing this for the very first time. We are the math pioneers who are saying, hey, we need an inverse function. We want to be able to undo exponentials. Let's make something up. Let's create the inverse. So, what do we have? And maybe we'll get some motivation from other types of functions. For example, like I kind of just wrote here, we had the function x cubed, and we would want something to denote. We want to make up a symbol that would denote the inverse of this. And what someone came along and said is, let's call them roots. Why? I don't know, that's what they called them. And they used this symbol. They said, this is the symbol that'll mean the opposite or the inverse of raising something to a power. We'll call it a root, and we'll put a little 3 here to remind us that it's the inverse. Or, I don't know, if we have something like x to the 7th. Oh, well, we'll just come up with a notation for the inverse of this. We'll use this funky kind of symbol here, and we'll put a 7 there to remind us that these are inverses of one another. Let's do the same thing. Let's do the same thing with exponentials. So, we have an exponential function, f of x. Let's say it's 2 to the x. Or maybe we have a different exponential function. Maybe I'll call it g. Maybe it's 3 to the x. I don't know, maybe there's another exponential function. Maybe it's, I don't know, 1/4 to the x. Now, we just want to come up with a notation that would be the inverse of these. So let's just make something up. Well, by us making something up, I'm going to go with what mathematicians decide to make up. Let's just give a notation to what we're going to call the inverse. For whatever reason, let's call it, why not, a logarithm. So we'll use the word log. And so instead of having kind of this root symbol, we'll just say the word log means the inverse of an exponential. But we would like part of this notation to remind us that it's specifically the inverse of the exponential function that has a base of 2. So maybe we'll put a little subscript here and we'll write a 2 here. So we'll call this log base 2 and we'll put parentheses here. So we have an exponential function and we're going to have something we're going to call its inverse. We're going to give it symbol. We're just going to call it log. That's just its name. And we'll put a little 2 here to remind us that it's the inverse of this exponential function. So if we have this, here is our exponential function, 3 to the x. What should we denote as its inverse? Well, we'll put the word log, and then we'll put a 3 here, and we'll put an x. This is just reminding us that log base 3 of x is how we read this, log base 3 of x. The base 3 here reminds us that this is the inverse of the exponential function 3 to the x. This base is 3, this base is 3. Or, what would we denote as the inverse of this function? Well, we put the word log, and we put a 1/4 here, x. Now we're just making up a notation for the inverses of these functions. We could have came up with a different symbol. Maybe we said maybe we made up the symbol. It's a cool swirly with a 2. This is the inverse of 2 to the x. We could have said, oh, this is swirly of 3. This is swirly of 3, which is just something we made up that would denote the inverse of this function. Or maybe someone said, oh, the inverse of 1/4 to the x is swirly of 1/4. It's all just convention. Well, I wasn't the one who made it up. By convention, the symbol we use for the inverse of an exponential is a log. That's just the symbol we use. Okay. Okay, so let's talk about it more in general. Let's talk about the notation here more in general. I'm going to erase a little bit of this what we have here. These are called logarithmic functions. They're just inverses of exponentials. So if you're ever walking down the street, and someone just kind of hops out at you and they say, oh man, these logarithms, these functions, these logs, I just don't understand them. What are they? Could you explain them to me? What would you say? They're like, oh, well, they're just inverses of exponentials. Logarithms, that's all they are. They're inverses of exponentials. Just like how the cube root is the inverse of x cubed. So that's how I would explain them. What are logarithms? They're inverses of exponentials. Okay, so in general, if we have a function b to the x, this is an exponential function. There's conditions on this. B has to be greater than 1. B has to be greater than 0. B cannot be 1. We're going to choose to denote its inverse as log. That's just the symbol mathematicians decided to use. And then we'll put a little b here and an x. We read this as, we would say, log base b of x. Okay? So this is what we're denoting as the inverse, and so since the log base b of x is defined to be the inverse of this exponential, since this exponential function had conditions on the b, log base b of x also has those same conditions. We would also require for the base of a logarithm for b to be greater than 0 and for b to not be equal to 1. This is a logarithm function. Okay. So a good thing to note here, and we'll talk about this here in a second, is that when we're talking about exponentials and logarithms, the base of an exponential is the same as the base of the logarithm. Okay, cool. Okay, so let's talk about these functions here in just a little bit more depth. Okay, what would be some nice properties of these functions? Okay, so for example, I kind of wrote this on the board not too long ago, but if we have a function f of x, which is equal to x cubed, its inverse is the cubed root of x. Now there's a special property with functions and their inverses. Remember we learned when we take a function and we compose it with its inverse, well, what happens? We just get out x. Similarly, if we do the opposite composition, this will also be x. Now, how does this look visually? What are we doing? We're taking the cubed root of x, and we're cubing it, so we kind of think, when we're seeing this, that these cubes kind of cancel each other out. Or these 3's cancel each other out, we're just left with x. Over here, what would this look like? This looks like we're taking x cubed. We're taking x cubed and then cube rooting it. So even in the opposite order, we would still think that these 3's cancel each other out, and we'd still get out x. Okay, this is exactly how it's going to work with our new notation. It's exactly how it's going to work with our new notation with exponentials and logarithms. So for example, if we have a function f of x which is equal to 3 to the x, and we are going to denote its inverse to be log base 3 of x, well, when we compose these functions together, because they're inverses, they cancel each other out. So what does that visually look like? So let's first do f inverse of f of x. So we just want to visually see what this looks like. So f inverse, what's f of x? F of x is 3 to the x. So now I'm going to replace the x in the log base 3 of x with a 3 to the x. So we'll get a log base 3 of 3 to the x. These are inverses of one another. So we want to kind of mentally think, just kind of how we cancel things here, that these 3's cancel each other out and we're just left with x. Similarly, if we had a function f and we can plug inside of it f inverse, just going to kind of look the other way, or everything's going to be swapped. So this would be the same thing as f. We'd be plugging in log base 3 of x. So wherever I see an x in f of x, I'm going to replace that with a log base 3 of x. So this x gets replaced with log base 3 of x. So we write a 3, and in the exponent we'd write log base 3 of x. These are inverses, they cancel each other out. You're still going to kind of imagine that these 3's cancel each other out, and we're going to get out x. So really, we haven't learned anything really new besides just a definition. I'm just applying what inverses do one another, and I'm just presenting it how aesthetically it looks when these functions are composed with one another. Okay. So in general, if we have f of x, which is equal to b to the x, and we have its inverse, which is log base b of x. If you ever see out there, if you're out there and you ever see this kind of thing just out there in the mathematical wild, if you saw something, you know, I don't know, log base b of bx, if you saw this floating around, you would say, oh, hey, aren't those just inverses of one another? Don't they just cancel each other out? Yes. Yes. Similarly, if we ever see a b to the log base b of x, if you see this out in the wild, you would say, wait, aren't those inverses of one another? Yeah, they just cancel each other out. So that's how aesthetically we can see an exponential and a logarithm kind of combined together in a composition for them to cancel each other out. So I'm really not doing anything different here than saying that the cubed root of x cubed is x, or the cubed root of x cubed is x. I'm doing the same exact thing, just with a different notation. Okay, now, there are two very special logs that we should talk about. There's two very special logs that we should talk about. So, special logs. Okay? They have to do, one, if we have a function f of x, and a nice, I guess, important base for an exponential would be base 10. Why is base 10 an important base? Well, we have a base 10 number system. I don't know, we have 10 fingers. And what we denote as its inverse, since this is an exponential function, we would write log base 10 of x. But it's very common that we do not write the 10. So we actually instead, it's very common to not write this. We would instead just write log of x. So if there is no base here, it's just assumed that means log base 10, which just means it's the inverse of the exponential function with base 10. Okay, this is very familiar, or should kind of be familiar, for example, when you think about the square root function. So when we think about the square root function, technically, since, I don't know, the square root, the base 2 root or the square root is so common that we don't normally write a 2 there, so we just kind of leave it, and it's just assumed if we don't see anything on the radical that this means the square root. It's very similar. Okay, so if it's log base 10, you'll just see the word log. Also, what's another super important, I guess, base of an exponential? E! E! This is also another super important base for an exponential. The number e is super important. You're going to see this pop up all over the place in calculus. So e is a very special number in math. And so it has a very special, or e to the x is a very special function in mathematics. So when we think about its inverse, we would write log base e of x. But since it's so common, we usually don't write log base e. We just write ln of x. So this means natural logarithm, ln. So I'm going to write that. The way you would pronounce this is you might see some people say the natural. This is the natural logarithm. But you'll actually hear most people say ln of x. They'll say ln of x. That's how they'll say it. ln of x. What is ln of x? That's just the logarithm base e. What is logarithm base e? It's the inverse of the exponential function e to the x. Okay, so you'll actually, if you ever look at your calculator, you actually only have these two logarithms on there. Notice here on your calculator, you have a log button. Notice there's no base. This is log base 10. And if you look in blue right above it, it says 10 to the x. There's 10 to the x. Below it is its inverse, log base 10. Below here, you see an e to the x in blue. Its inverse is log base e, but we denote that with ln. So those are actually the only two logarithms you have in your calculator. Okay. So, natural logarithm ln. Now, well, why is it ln instead of nl if it's natural logarithm? I think because in French, I think it might be the French mathematicians who came up with this. Don't quote me on this, but from my understanding is they pronounced it logarithm L natural or something like that. So that's why it's ln, but we say natural logarithm. Okay, so what we're going to do here is, I don't know, we've been kind of doing just a lot of definitions. But one very useful thing to do with exponentials and logarithms is switch forms. So a great tool is switching forms. Switching forms. Okay. So there's something that's called an exponential form. And there's something that's called a logarithmic form. Okay? If something is an exponential form, it has the form y is equal to b to the x. So, for example, this could be like, how about 2 cubed, let's do 3 squared equals 9. So this would be something in exponential form. What would this be in logarithmic form? This would be that x is equal to log base b of y. This is the logarithmic form. Okay, so this would read over here, that 2 is equal to log base 3 of 9. Okay, so let's kind of compare what this is saying, and I would like to kind of compare it also to how you think about square roots. How do you read this? This would be saying, like, let's pretend that I didn't have the 2 here, for example. We have log base 3 of 9. What does this mean? This reads 3 to what power gives you 9? 3 to what power gives you 9? 2. So that's why, because log base 3 of 9 is equal to 2, because 3 to the power of 2 equals 9. And that's how we should read it. These say equivalent things. When we're seeing log base 3 of 9, this is again asking 3 to what power gives you 9? Well, 3 squared gives you 9. 3 squared gives you 9. They're opposite operations. This would be the same exact way you would think about how you talk about square roots. Like, for example, how would you explain to someone that the square root of 16, how would you say the square root of 16? Why would you say it's equal to 4? Well, what do you do with square roots? When you're trying to explain someone, what's the square root of 16, you'd be saying, what number do you multiply by itself twice to get 16? Well, 4. Why? Because 4, think of there being like a 2 here, because 4 squared is equal to 16. So this would be like power form, and this would be like root form. So it's a very similar idea. Okay, very similar idea. Okay, so it's oftentimes good to be able to switch forms. Now the key thing I remember about exponentials and logarithms is what you should always pay attention to is that the base of the exponential is the same as the base of the logarithm. Now, what are logarithms? Logarithms are exponents. Logarithms are exponents. So here is the x, the logarithm, the log base b, the logarithm is the exponent. It is the exponent. Notice over here how this reads. This says 3 to what power gives you 9? 3 squared gives you 9. So what logarithms are the exponents. So I remember those two things. I remember that the base of the exponential is the same as the base of the logarithm, and that logarithms are exponents. Okay, so let's go ahead and just do a little bit of practice with switching forms. And then I'll show you why it's so useful. Switching forms. Okay, so for example, if we have log base 4 of 64, this is equal to 3. Why is log base 4 of 64 equal to 3? Well, what does a logarithm say? This says 4 to what power gives you 64? It's telling you that it's 3. So this says the same thing, that 4 to what power gives you 64? Well, 4 cubed gives you 64. So I've switched between logarithmic form to exponential form. Similarly, if we had log base 5 of 1/5 is equal to -1, what is this saying? This is saying 5 to what power gives you 1/5? Well, 5 to the -1 power gives you 1/5. I hope this makes sense. Anything to the -1 power is just 1 over. So here, we've switched from logarithmic form to exponential form. So we went this way. Okay, if we're going the other way, let's say we start with 6 squared is equal to 36. Let's write this in log form. Okay, well, the base of the logarithm is the same as the base of the exponential. So this would be saying 6 to what power gives you 36? 6 to what power gives you 36? 2. 2. Okay. One more. What if we have 3 to the 2x is equal to 10? Well, if we want to switch this to logarithmic form, we should remember that the base of the exponential is the same as the base of the logarithm. Okay, logarithms are exponents. Logarithms are exponents. And then we'll write the 10 here. This says 3 to what power gives you 10. In this case here, we're saying 3 to the 2x is equal to 10. So this is almost like an equation. Well, this is an equation. And we'll see here pretty soon what's great about switching forms. Well, if we're able to evaluate this, I could easily solve for x here, so I'm able to solve this equation. Woo! That's what we want to be able to do. Okay, so I'm going to put a couple problems up on the board, and I just want you to pause the video. I want you to pause the video and switch forms. So on this left-hand side, we'll have log form, and on the right-hand side, we'll have exponential form. Okay, so let's say over here, we have log base 2 of 1/8 equals -3. Log of 3 equals 2t. Let's say we have 7 cubed is equal to 343. Let's say we have the natural log of x plus 1 equals 2. Let's say we have 10 to the -4x is equal to 0.1. And how about e? E to the 0.5x is equal to t. So go ahead and pause the video and switch this to exponential form, switch this to exponential form, switch this to log form, switch this to exponential form, switch this to log form, switch this to log form. Give it a shot. All right, let's do it. Okay, over here, the base of the exponential is the same as the base of the log. This says 2 to what power? 2 to what power gives you 1/8? Well, 2 to the -3 gives you out 1/8. And this should make sense. What does 2 to the -3 mean? That means 1 over 2 cubed. Well, 2 cubed is 8. So this should make sense. Okay. Over here, this one's a little bit tricky because we don't see a base here. Remember, if we don't see a base, we assume that this is log base 10. So this will be 10 to the 2t is equal to 3. Okay. Over here, we want to write this in log form. So the base of the log is the same as the base of the exponential. So log base 7 of 343 is equal to 3. This reads 7 7 to what power gives you 343? Well, 7 cubed is 343. You know, if you can't do 7 cubed in your head, we should check this with our calculator. Is it true? And I hope I just didn't write some garbage down on the board. 7 cubed is 343. Cool. Okay, so we just switched forms. Okay, how about right here? Well, here I have natural log. So what does that mean? That's log base e. So this means e to the power of 2, remember logarithms are exponentials, would be equal to x plus 2. Oh, sorry, x plus 1. Okay. Over here, this is a base 10, so I want to have log base 10, so we'll just write log of 0.1 is going to be equal to negative 4x. So here we have 10 to the negative 4x equals 0.1 in logarithmic form. Okay. This last one here, we have log base e. Remember we denote that with natural log. So we have the natural log of t. E, we would say e to what power gives you t? Well, it's saying e to the 0.5x. E to the 0.5x would be equal to t. So here we are switching to logarithmic form. Okay, so it's going back and forth. Now, while it's great to be able to switch forms like this, really what's kind of going behind the scenes when you're actually switching forms, really you're just applying the inverse function to both sides. So let me show you what I mean. So why is this working? Why is this switching forms working rather than just kind of, I guess, reading or understanding in English what a logarithm means? When you're switching forms, you're really just applying the inverse function to both sides. Let me show you what I mean. So if we have that y is equal to b to the x, let's apply the inverse functions to both sides. So I'm going to write it down here. So y would be equal to b to the x. Well, if we apply the inverse to both sides, log base b, that's its inverse. Well, what happens? The b's cancel each other out, and I'd just be left with x. And over here, I would have log base b of y. Notice what I've done here. I basically just went from exponential form to logarithmic form. How did I do it? I just applied the inverse to both sides. That's really what you're doing when you're switching forms. Or if we wanted to go the other way, if we have log base b of y is equal to x, well, we'll compose this inside the exponential that undoes a logarithm. So you kind of put this in the power, so it would be b to this. These b's cancel each other out, so it would just be y is equal to b to the x. So when you're switching forms, really you're just applying the inverse function to both sides. Okay, now here's the question. Why do we care about switching form? Why do we care about switching forms? Well, it helps us solve equations. It helps us solve equations. That's why it's so great. We can solve equations. That's why it's great. Switching forms, this is why we care. Switching forms helps us solve equations. Okay, let me show you what I mean. So for example, let's say we wanted to solve the equation log base 3 of x is equal to negative 2. Let's say we want to solve this equation. Well, a lot of us are kind of unfamiliar or don't have as well of a grasp of what a logarithm, I guess, means, or just reading this. So what do? Just write it in a different form. Just like when you say to someone, hey, the square root of 16 is 4. Why? Because 4 squared is equal to 16. So reading this logarithm might be hard for us to understand, so if we switch forms, maybe it's a little bit easier. What is this saying? Well, this is saying 3 to the power of negative 2 is equal to x. I just went from logarithmic form to exponential form, and now we can solve this equation. This is 1 over 3 squared, or x would be equal to 1/9. Sweet, we were able to solve this logarithmic equation by switching forms. Let's do another one. let's say we have log base x of 25 is equal to 2. Maybe we want to try to solve this equation. Well, it's kind of maybe tough for us to be able to see what's going on here. So maybe we just need to read what this means or switch forms. This is saying that x to the power of 2 is equal to 25. So now we could solve this equation. So what we could do here is we could apply the inverse function of both sides. What's the inverse of x squared? It's the square root, but we got to be careful. Remember, x squared isn't a one-to-one function. So this could be the plus or minus. So I have to do the plus or minus. So x could be plus or minus 5. If you don't like how I solved this equation by applying the inverse to both sides, something kind of fun here when we're solving x squared equal to 25, if you subtract 25 from both sides, this would be the same thing as x squared minus 25 would be equal to 0. Now this is a quadratic equation. You could use the quadratic formula. No, don't do that. You could factor this. Difference of squares. X minus 5, x plus 5 is equal to 0. So what are the solutions? Well, x could be 5 or x could be negative 5. We're getting both. Either way you want to think about it, we're getting the same answer. Okay, but be careful. Is x equal to 5 and x also equal to negative 5? Are these both good solutions? No. What is x? X is the base of the exponential. Remember, we have conditions on the bases. X is the base of the logarithm, and remember we have restrictions on the base of a logarithm. The logarithmic bases have to be greater than 0. In this case, we can't have x be equal to negative 5. X will just be 5 in this case. And that just comes from the condition we have on the base of a logarithm, which came just from the condition of the base for exponentials. I'm going to put 2 on the board. I want you to give it a shot. Try to solve them. Okay. So let's say we have log base x of 6 is equal to 1/2. Try to solve this equation. Also try to solve the equation, how about log base 3 of x equals negative 4. Go ahead and pause the video and try to solve these on your own. Okay, let's do it. So we're going to switch forms for both of these. This says x to the power of 1/2 is equal to 6. Okay, now how do I undo this? Remember x to the 1/2? X to the 1/2 just means the same thing as the square root of x. So how would we undo this? Well, what's the inverse of a square root? Squaring. So either form here, if you want to square, we'll get the same answer. So if we square both sides, I'm just kind of aesthetically showing you different ways to see this. Well, if you think about how exponent rules work, this is x to the n is equal to x to the n times m. Well, this would be x to the 1/2 times 2, but 1/2 times 2 is just 1. So over here, this would read x to the first power is equal to 36. 6 squared is 36, or x would just be 36. And here, you could think that the square root and the square cancel each other out, and we still get 36. So I guess what's nice here is just kind of showing you why it makes sense that a square root is the same thing as x to the 1/2 power. So the solution to this one is 36. Okay, for this next one, same thing. We're just going to switch forms. This is saying 3 to the power of negative 4 is equal to x. So this means x. What does a negative exponent means? This means divide by 3 4 times. I don't know what 3 to the 4th is. Let's see. 3 times 3 is 9. I got 2 extra 3's. 9 and 9 is 81. So this is 1 over 81. So x is 1 over 81. And that's what we have. Notice, though, that I've given you, when we're solving, I guess, this kind of simple logarithmic equations, I've put the x's in 2 spots, but not a different spot. I put an x here, I put an x, I guess I put an x as the base, I put an x as the argument, but I didn't put an x as to what it's equal to. How could we solve those type of equations? Okay. Okay. Let's say that we have log base 2 of 16. Okay. Maybe what you could do here, a way to think about this is, what I'm going to show you here would be a way that you could evaluate a logarithm. I want to know what log base 2 of 16 is. Maybe we don't know what it is. Maybe we'll call it x. I want to know what the output of this function is. I take log base 2, I plug in 16, what would be its output? Well, what does this notation mean? This means that I want to know 2 to what power gives us 16. Now from here you might be able to guess what x is, but I'd like to show you kind of a nice algebraic way to solve something like this. So what we want to do here, if I'm trying to solve this exponential equation, well, it'd be really nice if I could have both sides of the equation have a base of 2. So for example, I have 2 to the x. Well, can I rewrite 16 as 2 to some power? Well, let's think here. So 2 times 2 times 2 is 4, times another 2 would be 8, times another 2 would be 16. So this is the same thing as 2 to the 4th. So I have an exponential function on the left and an exponential function on the right. They have the same base. The base on the left is the same as the base on the right. So what can we do? Boom, 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 boom. We can drop the base. We can drop the base. This is a bad dubstep joke. Boom! If we have two exponential functions and they have the same base, boom! Drop the base. Drop the base. So here we have that x is equal to 4. We have x is equal to 4. So the dropping the base method. Okay, this is great. This is great. Let's do another example. Let's do another example. Let's say we want to do log base 5 of 125, and we want to know what the value of this is. Similarly, maybe we're trying to figure out what is log base 27 of 9. Go ahead and pause the video. Write these in exponential forms. See if you can make both sides of the equation have the same base, and boom, drop the base to solve the equation. Pause the video, give this a shot. Let's do it. Let's do it. What does this say? This says 5 to what power gives you 125. Okay, well, let's think about it. So let's see, 5 times 5 is 25. Times another 25, I think would be 125. So I think that 5 to the x would be equal to 5 cubed, and then boom, 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 we'd get x would be equal to 3. Careful with your booms. You don't want to be solving these equations too late at night. Your neighbors are going to be upset. Equation, x equals 3. That's the solution. Okay, over here. What is this saying? What is this saying? We want to know 27 to the x is equal to 9. That's what this is saying. This one here's a little bit trickier. This one's a little bit trickier. Why? Well, because I don't know what we can raise 9 to the power of, or I don't know how I can rewrite 9 as 27 to some power. That's a little bit tricky. It's a little bit tricky here. But what we can do here, which is different, is we can write both these bases as a base of 3. Notice here that 9, maybe I'll write it up here. Notice that 9 is the same thing as 3 squared. I hope you also believe that 27 is the same thing as 3 times 3 is 9. times another 3 is 27. 27 is the same thing as 3 cubed. So we can make a replacement. 27, how about we replace 27 with 3 cubed? And 9 with 3 squared. Ooh, now we're getting somewhere. Don't drop the base yet. Hold on. Our exponent rules say I can multiply the 3 and the x together. So this is 3 to the 3x is equal to 3 squared. 3 squared. Check the time. Okay, it's not 10 o'clock yet. Boom. Drop the base. Boom. Boom. Drop the base. We get that 3x is equal to 2. Divide both sides by 3. We get x would be equal to 2/3. X would be equal to 2/3. That's the answer. We have log base 27 of 9 is 2/3. Is 2/3. Now let's think about why this makes sense. Why does this make sense? I'm going to erase a little bit of what we have here. I just want to make sure I'm boxing and this is the correct answer. Okay, why does that make sense? Why is 27 to the 2/3 power 9? 27 to the 2/3. Well, this is how we should interpret what this is saying. This is saying, one way to think about what this is saying is this is the same thing as 27, and then we get 1/3 times 2. But using exponent rules, this is the same thing as 27 to the 1/3 power being squared. Or maybe I don't need parentheses right here. Doesn't matter. This is saying the same thing as 27 to the 1/3 power is 27 to the 1/3 to the 2. Well, what does 27 to the 1/3 mean? Remember, to the 1/3 power means cube root. So this is the same thing as the cube root of 27 all being squared. Well, what's the cube root of 27? The cube root of 27, what number would I multiply by itself 3 times to get out 27? 3. So this would be the same thing as 3 squared, which is 9. Which is 9. It works. Beautiful. Okay. That's all I have for for today's lecture, or for this lecture on our introduction to logarithms. What is a logarithm? It's the inverse of an exponential form. Okay. We learned how to switch forms, and we learned how to use switching forms to help us solve simple logarithmic equations. What are we going to do in the next video? We're going to be thinking about the graphs of logarithms, and we're going to think about the transformations of graphs of logarithms. We'll see you there. Take care.